Okay, good afternoon. Why don't we get started? I know it's still a little early, but one thing I forgot to mention in the first lecture last week was that according to the syllabus, the last week, the reading, review, recitation, relaxation week, we're just going to dedicate to students who are taking EE130A, the graduate students, to give oral presentations on their projects. And during the oral presentations, I'll be asking questions. So that's one difference. Actually, that's the main difference between 230A and 130, in that the project will be slightly different. It'll be a little bit more difficult, the design project. And also, the students will be expected to give oral presentations. Everybody, of course, is welcome to attend the oral presentations. It might help the undergrads with their projects as well. Yes, question? OK, yeah, so everybody's welcome to attend the presentations. Okay, so that's really the only significant difference between EE130A and 130. OK, so last time it was a little bit rushed, so I apologize. I wanted to mention a few things. So I did post the notes, the marked lecture notes, online at the end of last Thursday evening, but I didn't explicitly write. So hopefully it's obvious. An amorphous material has no long-range order. A crystalline material does, and that's why you can define a unit cell to describe the structure, the lattice structure of the crystalline material. So we last time mentioned that there are some typical metals, highly conductive materials, aluminum and copper, used in integrated circuits. And I forgot to mention that the most common integrated insulator used in integrated circuits today is silicon dioxide. Okay, so that's highly insulating. It's in the upper range of the resistivity, 10 to the 18 ohm centimeter. Okay? And for an undoped semiconductor, the pure semiconductor, the resistivity is 10 to the 4. OK, so I didn't explicitly write, but this is the unit cell of a single crystalline silicon crystal. Oops, OK. And I know I went over this quickly, but Peng this week, during the discussion sections, we'll go over some examples for coming up with the Miller indices for different planes and different directions. And you will have to go through this exercise for the homework problem set. Okay? I sort of highlighted here. You just take the intercept as a function, as a multiple of the lattice constant. And in this class, really, all you have to know is the family of 100 planes, 110 planes, and 111 planes. That's all you need to know for this class. Okay? Now, so last week, so there's, if you look at the website, if you visit the class website, there actually is this link here to cool educational applets. I don't know if you think it's cool, but anyway, one of these. So if you go to this page, and the reason I didn't show this last time is because this website was down last Thursday, so I couldn't really show it to you. But basically, if you click on this link over here to look at the unit cell for different semiconductor materials, this is what you get. And so it's an applet, so you can actually move the unit cell for silicon around, so you can show the bonds or not, right? Okay? And that's what I had in the lecture slides. So the reason why you can just specify a family of planes, like a 100 plane, family of planes, if you look, it doesn't matter which face of the cube you look at, basically the arrangement of atoms looks the same. So that's what I mean by a family of equivalent planes. So this view is what you would see looking at any 100 or 010 or 001 plane. And this view here is the same view as this view here, right? There's all within the family of 110 planes. Okay, and so on. All right. So yeah. So sorry. Unfortunately, this website was down last week, but it's up now. Okay. Let's see other points of clarification from last time. So last time we introduced a simple bonding model for a semiconductor material, silicon, and today we'll introduce a more sophisticated model. But in case this is, I know this is not typical chemistry convention, but what this illustrates is that each silicon atom, we just draw a core with the 10 electrons circling around the nucleus, and then only the outermost valence electrons, 4 per silicon atom are available for participating in covalent bonding. So if you look at any silicon atom in this picture, in this bond picture, basically you could pick like 4 that were contributed by that silicon atom, and then the other 4 around it are contributed by its 4 nearest neighbors. Okay, so this is the simple bond model where we can show electrons and holes moving around. And we want to keep track of electrons and holes because those are the charge carriers that conduct current in an integrated circuit device. Okay? So I added these after the fact last time. But basically, a hole can basically has a positive charge associated with it. Because if an electron leaves a covalent bond, as illustrated here, let's say this silicon atom number 1 has net positive charge because one of its valence electrons left. Okay, so let's say that valence electron wanders away somewhere else in the lattice. So this atom number 1 has some net positive charge at that location. But an electron from a neighboring covalent bond over time could move into that spot, participate in that covalent bond where the hole is. And that would mean that if an electron, this label number 2, if event number 2 occurs, that means an electron's moving from a neighboring covalent bond to fill that spot in the, that was left behind when an electron left, right? So in step number 2, an electron from a neighboring covalent bond moves into that half-filled covalent bond. So leaving behind, so now the half-filled covalent bond has moved to position number 2. So the positive charge associated with that half-filled covalent bond has moved to atom 2. And this can happen again with event number 3. A neighboring electron, an electron in a neighboring covalent bond moves up into that half-filled covalent bond. And now you end up with a hole, a half-filled covalent bond at atom number 3. So as electrons have moved from site 3 to site 1, basically the hole has moved. And the positive charge associated with it has moved from location 1 to location 3 in the opposite direction. Okay, so a half-filled covalent bond is also mobile. That's the bottom line. And so since it has positive charge associated with it, we call it, we keep track of it as a mobile charge called the hole. Okay? Okay, so I wanted to demonstrate this. That's why I asked Peng to sit here. Okay, so Peng's going to illustrate the process of an electron leaving a covalent bond. Oh, we have a long row here. Okay, so go ahead. I'm just kidding. So Peng stands up. All right, so let's say he's the electron. He's mobile. He can move around in the room. Okay? And that's a half-filled covalent bond, this empty seat. So I'd like you to take your books. All right. And then walk to the back of the row. And then, can you move up? So this is modeling an electron from a neighboring covalent bond, filling so the half-filled covalent bond moves here, right? So a positive charge. Okay, why don't you move up, and I'll give you all a souvenir for participating. Actually, I don't think I have enough, but anyway. So last time I showed you a wafer, right? So I figured some of you might want a souvenir as a wafer. Or there's a Frisbee for those of you who aren't really interested in. And Global Foundries is one of the major semiconductor manufacturing fabs. So take one and pass it on. You can take the Frisbee or the, or the wafer. But anyway, so you see, OK, now Peng can sit back down. That's called recombination of an electron-hole pair. Right? So if Peng actually sits down in a chair, you end up with no easy wafer. Like he's not moving anymore, right? So there's no electron moving, and neither is there a hole moving, right? OK, so basically people can move either through chairs, just like electrons can move through half-filled covalent bonds, or they can just move by standing around in the room, just like a free conduction electron moving around in the lattice. Does that make sense? OK. All right, so that's the bond model. Okay, and of course, as you heat up the seat, more likely that somebody's going to stand up and move around. So the concentration of electrons and holes will increase actually exponentially with temperature. Okay? So one thing is that so Peng will do this in the discussion, sort of show you if you want to change the temperature by, let's say, 10%, plus or minus 10%, the electron and hole concentrations change by much more than 10%. And that's what we mean by being very sensitive function of temperature. Right? If you change the temperature a little bit, but the concentration changes a lot, we say that intrinsic carrier concentration is very sensitive to temperature. Okay, so that's the bond model. And here's another sort of analogy for a bond model. Right. Okay, so are any of you familiar with the game Pachinko? Right, so you have like posts in a board, and you have balls that move through the board, and ideally you make the balls fall into some containers to win points or money. So here's a cartoon, just a schematic illustration of a Pachinko board, where we have balls moving around, mobile balls like electrons moving around the lattice. And you have bollards, so fixed points, where they bounce the electrons. I mean, the balls bounce off those fixed points, bollards. Okay, so the question here is, how can you tell which direction the balls are moving? Gravity. How can you tell by looking at this which direction gravity is? You can't. Yeah, exactly. So this is analogous to a bond model. Some information is missing. You need to know how electrons and holes move in a semiconductor material. You need more information. You need to know something about the potential energy and the potential energy of the system, right? So that's exactly what the point of a band model is. Okay, so today we're going to go over the energy band model. We'll get there in a few slides. Okay, so the energy band model helps us keep track of not only sort of the concentration of electrons and holes at any point in a semiconductor device, but it also tells us, which direction electrons and holes are going to tend to move. Right? Just like gravitational potential will tell you, if you knew the gravitational potential as a function of position on the Pachinko board, you would know which direction the balls will be moving. Same thing, if you know the electric potential of electrons in a semiconductor material, then you'll know which direction they will tend to drift. Okay? Okay, so that's the idea. All right, so to derive the energy band model, we have to sort of start again from a single atom. Okay, so in a single atom, on the upper left here, this is a plot of the potential energy of an electron as a function of position. And this is kind of a radially symmetric system. So you have a nucleus that's positively charged and an electron orbiting around it. The closer the electron is to the nucleus, the positively charged nucleus, the less potential energy it has, right? The farther it is away, the more. And basically, the potential increases as an inverse of the distance away from the nucleus. Okay, so, and then from physics, you know that there are only certain allowed energy levels that the electron can have when it's orbiting around the nucleus. So that's the situation for a single atom. If you bring another atom close by, then the potential of one atom can start to affect the potential profile in the other atom. And so it's really the uppermost allowed energy levels that get affected first, most easily first, right? The electrons that are least likely tightly bound to the nucleus, those energy levels will be affected more easily by atoms that are getting close. Okay, so that's the idea for the upper right picture there. So this is something we call the Pauli exclusion principle, that two electrons in the same system can't have the exact same quantum numbers. So when they're individual, the energy levels in individual atoms, when the atoms come close together, the individual energy levels have to split a little bit or move in energy, so they're not exactly the same. So basically, you end up with discrete allowed energy states that are very closely spaced when you bring other atoms close to a single atom. Oops. Okay, so if you have a large number of atoms, capital N number of atoms, let's say this is the surface on the left, surface of the crystal, and then you have many atoms all nicely arranged in a lattice. Basically, this energy level splitting that I talked about earlier happens more and more, and you end up, rather than with a single, let's say, allowed energy level, let's say E2 or E3 for a single atom, you end up with a band of closely spaced allowed energy levels. And those energy levels belong to the entire crystal lattice. Okay, it's not, it doesn't, none of those states are tied with one atom. Okay, so you have many allowed energy levels within a small energy band, range of energy levels. Okay, so this is basically what's illustrated in the PRA textbook. If you look at the electron energy and see how you evolve from, okay, so in an isolated atom, you have this 3s energy level, and you have 3p, right? And the total number of electrons in these two levels is 4. And then as you decrease the spacing, so you end up with a lattice of silicon atoms closely spaced together, you end up with, okay, I can't really draw it out here, but you end up with, rather than 2 energy levels, you have 2, let me just draw it better. Separate bands of allowed energy levels. Does that make sense? Okay, so you end up with, okay, so here are 6 states allowed in the 3p orbital, and then 2 states allowed in the 3s, and you end up with 4n and 4n. Yes, n is the number of atoms. Okay, so that's kind of what's the intent here, is that as you bring atoms, as you decrease the average atomic spacing from isolated atoms to just a single crystalline silicon lattice, you end up with 2 bands. That's basically these 2 bands right here. Right, so you have a band of allowed energy levels here that electrons can occupy, another allowed energy, a band of energy levels here. And because generally electrons tend to try to usually occupy the lowest available energy states, most of the states in the lower band are filled at any point in time, and most of the states in the upper band there are empty. That's why well, it's kind of extreme case. 4n empty states and 4n filled states. Okay, so this band of allowed energy levels is called the conduction band, and the band that's mostly filled is called the valence band. Okay, so it's just a band of allowed energy levels that electrons can occupy. So in the example, the bond model, we have electrons participating in covalent bonds. Okay, so this represents all the energy levels or energy states of electrons in covalent bonds. And the conduction band then represents the allowed energy levels for electrons that have escaped a covalent bond. So this is what we call conduction electrons. Or for short, probably from now on, we'll just call them electrons for short. Okay? Okay, does that make sense? So bottom line is, instead of discrete energy levels, you have bands of discrete energy levels. But the energy levels are so closely spaced that it's very easy for an electron to move from one allowed energy level in the valence band to the next. And also similarly in the conduction band, if an electron is in the conduction band, very easily can move between allowed energy levels in the conduction band because they're just so closely spaced together. Okay? Okay, so valence band and conduction band. Those are things you should remember. So we don't really want to draw bands. Really, this is too hard to draw. I mean, too cumbersome to draw. So the only thing that's really important is the edge of the valence and conduction bands. So we only need to keep track of the upper edge, the highest energy level in the valence band, and the lowest energy level in the conduction band. Okay? So that's basically an energy band diagram plots electron energy. Okay? Electrons are negatively charged, so that's why on the next slide we'll talk about voltage, which flips the polarity. Anyway, we're plotting energy of electrons as a function of distance in your semiconductor. And so this is a simplified version of the energy band model. And this difference here is the energy band gap, or the band gap energy, E sub g. Okay? And we'll give you the values of E sub g for different semiconductors in a subsequent slide. So just to review, these are the above EC, you have allowed energy states, and they're mostly empty. And below E sub v, you have allowed energy states, mostly filled. Okay. Yes, question, Ali. Distance from what? That's the question. Well, just location. Let's say location within the semiconductor. Sorry, so more precisely, this is a plot of electron energy versus location. Okay? Good question. Okay, so how do we illustrate? So that's so the allowed energy states. How do we show electrons and holes? These charge carriers. Okay, here's the energy band diagram again. We illustrate an electron, if we want to keep track of a specific electron, by drawing a dot on the energy band diagram. So in this case, we have an electron occupying an allowed energy state within the valence band. And to illustrate electron-hole pair generation, like when Peng stood up, he actually occupied an allowed energy state as a conduction electron. Okay, and then leaving behind an empty state in the valence band, and that's why we use an open circle. But that's a hole that can now move within the allowed. So remember, a hole moves due to electrons moving from one covalent bond to another. So a hole can move around within the valence band, just like an electron can move around within the valence band. Electron can move around within the conduction band as well. So electron basically can occupy states above E sub c. Okay? So conduction electron on the band model, in the band model, is just shown as a dot in the conduction band, and a hole is modeled as an empty state in the valence band. Okay? So to keep track, the E sub c is actually the potential energy represents the potential energy of the electron. And so the distance above E sub c, so this is a plot of electron energy, so that dot, if an electron is occupying an energy level where that dot is located, then it's going to have potential energy and kinetic energy equal to that level of energy. So if the conduction band edge represents the potential energy, then the distance above the conduction band edge represents the electron's kinetic energy. Okay? Now, holes are positively charged, so they're opposite sign as the electron. So if we wanted to plot qualitatively hole energy on this plot, then hole energy increases as you go down in this band diagram. And so the distance between the hole energy and the edge of the valence band edge, that represents the kinetic energy of a hole. Okay? So potential energy, just like gravitational potential, has an arbitrary reference. Okay? So it really doesn't really make sense saying, oh, my potential energy is such and such. It's really like my potential energy relative to sea level, right, might be something. So same thing in the semiconductor device. There's always going to be some reference energy level for potential energy. So in an electronic circuit, we usually set the reference potential at like ground, for example. So in this simple example in the upper left, we have a piece of semiconductor, and we apply a voltage across it. So the potential difference is 0.7 volts. Or you can say that the potential at the left is 0.7 volts relative to the potential at the right. Right? So the only thing that makes a difference is potential energy relative to some reference. So here, the reference would be ground. so we can plot the electric potential as a function of distance or location in this sample. So it starts at 0.7 volts on the very left side and goes down to 0, the reference level, on the right side. And so the potential energy, because the electron is negatively charged, is going to be equal to minus Q, this is charge on the electron is negative, times the electric potential. Okay? So if we remember from the previous slide that the potential energy is given by that conduction band edge for an electron, then we can actually write an expression for electric potential as a function of the conduction band edge location energy. Okay? So that's basically that. So bottom line is, if you have a voltage drop across a sample, that means you have an electric field, right? The voltage is changing with distance. So you have an electric field, and electric field is given by the rate at which the electric potential is changing, with distance. Okay, it's just defined, this is from physics, right? If you have a change in electric potential, you'll have an electric field. And so plugging in the equation above, this means that if you have an electric field existing within your semiconductor device that is exerting force on your mobile charged particles, that electric field can be visualized by a change in the conduction band edge. Okay? All right. So this is the energy band diagram then for a semiconductor. Right? So you still have the conduction band edge. Oops. Conduction band edge here on the left. Conduction band edge, valence band edge, allowed energy states up here, allowed energy states down here. But because of the electric potential that's being applied to this device, the electric potential is lower for electrons on the left because the electric potential is higher. Okay, so potential energy of electrons gets lower to the left and is higher to the right. Okay, so remember, electrons tend to like to flow downhill. Holes tend to like to float up in an energy band diagram. So this simple energy band diagram shows you that electrons will tend to move to the left and holes will tend to move to the right. Okay, so this is like the pachinko board. If you know the tilt of the board, you'll know which direction the balls go. It's the same thing here. Okay, and usually we illustrate an electric field by sort of drawing it like this. So there's an electric field here that's exerting force on the charged particles to move positively charged particles to the right, negatively charged particles to the left. Okay, and sometimes, okay, we call this terminology. We call this energy band bending, or just simply band bending. If the EC and EV are changing with position, then we refer to that as band bending. Like the bands are not flat. Okay. So one thing I forgot to mention is that this energy band diagram, this EG, that is a fundamental property of the semiconductor. Okay, so if the semiconductor material is the same over here to the left versus to the right, then the band gap energy is the same. Okay, so fundamental property. So in any energy band diagram, you should have EC and EV always spaced evenly. Okay? So what that means is that if you see a slope in the conduction band edge, you should see the exact same slope in the valence band edge. Okay? The separation between the band edges should always be equal to the band gap energy of the semiconductor material. Okay? Okay, and how do we measure that? In the past, scientists have shown light on semiconductor material and see what light passes through. And basically, at some point, electrons, if the photon energy is high enough, then electrons in the covalent bond electrons can absorb the energy and have enough energy to escape from the covalent bond to occupy an allowed energy state in the conduction band. So basically, you can keep increasing the energy of the photons, in other words, shortening the wavelength, until you start to see significant absorption. And that gives you an idea of what the energy band gap, band gap energy is. So for silicon, it's 1.12 eV. So this is a number that you need to either write down in your notes or remember. It shouldn't be too difficult, but yeah, that's, in this class, we primarily focus on silicon. Modern semiconductor devices do use a little bit of germanium, which has a smaller band gap energy. Okay, and then gallium arsenide has the largest band gap energy of these three dominant semiconductor materials. Okay, so we talked about bands of energy levels allowed. So the question is, well, okay, how closely spaced are those energy levels in those bands? Well, it turns out that the energy levels become more closely spaced as you go deeper and deeper into the bands. So for the valence band, as you go down lower in energy, the density of allowed energy states, the number of energy levels within a given like delta DE, like a given range, increases. And so we refer to the density, this density of allowed energy levels as G, as a function of energy. So little g, so this is G sub V for the density of allowed energy states per unit energy within the valence band. And in the conduction band, you call it G sub C, right, for conduction band edge. Conduction band. Okay. So if you plot the density of states, or the number of allowed energy levels within the small range of energies, it's like a milli-electron volts, plot that on a horizontal axis and plot versus energy. So first of all, you have 0 allowed energy states between in the band gap, right? So you can only have allowed energy levels either within the valence band or the conduction band. Anything in between, you don't have any allowed energy levels. Okay, so that's why you have 0 density of states between the valence band edge and the conduction band edge. But once you go into the valence band edge, the density of states increases, and same thing as you go up into the conduction band edge, the density of states increases. So for example, G sub C is proportional to the square root of E minus EC. So as you go to higher and higher energy levels within the conduction band, you have more and more density of states. And same thing for G sub V, proportional to EV minus E. Okay? Right, so as E goes more and more below E sub V, then you have more and more density of states. Okay, so a analogy is in the Memorial Stadium, in a football stadium, like the Memorial Stadium, at different levels, right? Like different levels far away. As you go farther and farther away from the field, higher and higher up, the number of seats within a certain range of level is increasing. Does that make sense? Okay, so the seats that are closest to the field, you have fewer number of seats per row. But as you go higher, you have more seats per row because, well, the circumference gets larger. Right? So this is the same thing. Similar thing is that the more the density, the number of allowed energy states within a given range of energies increases as you go deeper and deeper in the bands. Okay, so the spacing between these allowed energy states actually, this influence when you bring multiple atoms together and the potential influence of the atoms, that depends on the effective mass of the electrons. So the lighter the effective mass, the more energy level splitting you'll see. So if you have lighter electrons, well, effectively lighter electrons, then you'll have energy levels that are spaced further apart. This is like the quantization effect. So that's why the density of states actually also has a weak dependence on the effective mass. How do you find the effective mass? Oh, how do you define the effective mass, or how do you find it? Okay, I guess I can add that to the next lecture. So let me go over. It's actually in Professor Hu's book online, but I can add that slide to the next lecture as far as how do we practically measure the effective mass of an electron. But how do you define it? Or, well, okay. I think that's on the next slide. Okay, so first of all, for this class, use these values of effective mass for the purpose of calculating the density of states. Okay, So that's why this is subscript DOS. And this is where M naught, this is a standard free electron rest mass. Let me explain why the effective mass of an electron in a crystal is different than the effective mass of a truly free electron in vacuum. Oops, sorry, this is like minus 31. Okay. Okay. So, but just to quickly answer your question, basically we can use electron cyclotron resonance. So basically we can actually excite an electron at its resonant frequency and figure out the effective mass from this centrifugal, energy. So I'll have a slide. I'll add a slide on that for the next lecture. But in terms of effective mass, an effective mass of an electron in a crystalline solid can be either heavier or lighter than an electron moving in free space. Okay? So remember this electron potential diagram that I showed earlier to explain why the potentials of atoms start to interact with each other and resulting in energy level splitting, and you end up with bands of allowed energy levels rather than discrete energy levels. So basically, you have Schrodinger's equation that can describe this system where psi is the wave function that you can solve. But bottom line is this Schrodinger equation relates the total energy of a system it describes it as the sum of the kinetic energy and the potential energy. That's roughly, that's what the Schrodinger equation represents. So one way so most of the time, electrons moving in a semiconductor don't have a lot of kinetic energy. It's all relative. So relatively low kinetic energy. They're not moving all that fast on average. So it turns out that it's easier to solve this Schrodinger equation if we simply assume that there's no crystal. So the V, that second term, goes away, but we just modify the M. So instead of M naught, we have M star. And turns out that that's roughly a pretty accurate way to model electrons and holes moving around in a crystal if the kinetic energy is not very high. Okay? So essentially, we know that the effective mass in a crystal is different than an electron, but in free space. But if we exert force on it, it will accelerate. It'll have kinetic energy, 1/2 mv squared. It's going to be proportional to momentum squared, except this m has to be modified. Okay, and I'll mention next time how people experimentally find this effective mass value. All right, well, maybe I'll ask you. So why would an effective mass potentially be smaller than a free electron mass? That's usually the case in the semiconductor devices. The effective mass of an electron in a semiconductor material is usually significantly smaller than an effective of the mass in free space. Why might that be the case? Yes. Right, that's right. That's a good point. So you have ions. You have this crystal potential that might be helping to attract electrons to go from one atom, and then when you get there, like another atom is pulling on you. So that's right. You have all these positively charged nuclei that are helping to attract electrons to move around. So it becomes easier for an electron to move around in a crystal, depending on the crystalline direction, right? If there's lots of spacing between atoms, it's easier for an electron to move. If the atoms are really tightly spaced together, it can actually end up being more difficult for an electron to move in a crystal. So it really depends on the crystalline direction, whether or not you're distorting the crystal, and so on. But in most of the integrated circuit devices, yes, we take advantage. We orient the transistors to take advantage of the directions that have the lower effective mass. That's exactly right. So in Professor Hu's book, in his text, he calls it like surfing. It's like you have electrons that can surf over this potential, right, to help move the electrons around more easily. Okay. I think another analogy is when you go to a concert and, well, let's say if you go to a football game and you see a red shirt, you might pick up the guy and move him, pass him down, very, very quickly down to the field or something? I don't know what you do. Or do you pass them out of the stadium? I don't know. You pass them out of the stadium, right? So basically, all these people want to grab this guy and get him out, so it's very easy for him to move out among, all these people that are carrying him out. Okay? Okay, so in terms of the band gap energy, I mentioned that silicon has a band gap energy of 1.12 electron volts. How about other materials used in integrated circuits? Silicon dioxide, which is one of the best insulating materials that doesn't conduct electricity very well, has a band of allowed energy levels, bands of allowed energy levels, for covalently bonded electrons and free conduction electrons. But the band gap energy is very large, 9 eV. Okay, so later on we'll talk about, well, maybe next lecture we'll derive an equation for the intrinsic carrier concentration. But if the energy is so large between a valence band and conduction band, it's highly unlikely that due to just random thermal motion, then an electron will gain enough energy to escape a covalent bond. Right? So actually, maybe I should mention. So what does this energy, this band gap energy, represent in the bond model? Right, it's the energy needed to escape a covalent bond, exactly. So if the energy needed to escape a covalent bond is 9 eV, the chances are actually exponentially dependent on that energy, decreasing exponentially with increasing energy. So the chances that an electron would exist, electron-hole pair would be generated is vanishingly small. So there are extremely few electrons and holes that exist intrinsically in silicon dioxide. That's exactly right. A metal, on the other hand, let's say you have an allowed group of allowed energy levels in the valence band edge, and then you have allowed energy levels in the conduction band. And for some materials, these bands overlap. So you have no band gap. In other words, it's very easy for electrons to find a nearby allowed energy state to move into and move around freely in your material. Okay? Right. Any questions about the energy band model, how we illustrate potential, kinetic energy, and electrons and holes? Yes? Yes, okay, so the question was about the effective mass having a subscript. Yes, so, oh yeah, that's right, good point. M sub n, so n means represents negatively charged, so that's an electron. So M sub n refers to effective mass of an electron. DOS means this is the effective mass that determines the density of states. Next time we'll talk about a different effective mass that determines the conductivity. So you'll need to be aware and keep track of the correct effective mass to use in certain calculations. Okay, so M sub p, P stands for positively charged mobile carrier. That's holes. So this is the effective mass of a hole that's used for the purpose of calculating the density of states. So it turns out that the effective mass of electrons and holes are different in different directions if they're moving in different crystalline directions. And so you sort of have to take an average of the effective mass in the different directions to figure out how the energy level splitting. And it turns out that the way you take the average for density of states to determine the energy level splitting is different than the way you do it for figuring out conductivity. Okay? So this is a geometrical average. You take the product of the effective masses in the three x, y, z crystalline directions, and you take the cube root, essentially, okay, to get this effective density of states for the semiconductor. For conduction, we'll find out next time, it's you take the sum of the inverses, and then you have to multiply by some correction factor, and then you take the inverse. Okay, so it's just the way that you take the average. That's different. This is for conductivity effective mass is different, that the way you take the average effective mass versus for density of states? Okay, good question. That's a good question. So does the effective mass change as you go up higher in the conduction band edge, conduction band or the valence band? And the answer is yes, because this is an approximation to begin with, right? That you can actually just ignore the presence of the, where did I have that crystal? Yeah, this is an approximation. You're sort of ignoring the, or lumping the impact of that potential, electric potential, in the effective mass term. And like I said, this only is really an accurate way of modeling the electron wave function in a crystal for low kinetic energy. Yes, so as an electron moves higher up in the conduction band, this becomes less accurate. In fact, the effective mass does change in reality if you increase the kinetic energy. And it depends on which direction the electron moves. That's right. And if you're interested to learn about all these details, you can take EE130C, which is actually taught at the same time, unfortunately, this semester. But Professor Salahuddin is teaching a class on that. Okay. Okay. Any other questions? Yes. Why should the effective mass of the hole be different from the electron? Should we try that demo again? I have a race to see if Peng can walk up here faster, then you guys can all move down one seat at a time. I mean, which one do you think will happen faster? If Peng stands up and walks to the front of the room, or if that empty chair gets filled and moves up to the front? Same distance? Right. Generally, in general, holes move much more less mobile. They're less mobile than electrons. It's easier for electrons to move around freely in the lattice versus from one covalent bond to another. So an analogy I've used in the past is like you think about, Superman came out this weekend, this summer, right? So Superman flying around freely versus Spider-Man, who has to be attached to a building wherever he goes. Which one's more mobile? Right? That's another analogy. Now, of course, today there actually, it is possible. What we do in a modern integrated circuit is to enhance hole mobility, we actually can compress the semiconductor crystal to make the spacing of the atoms closer. So it's easier for a hole or an electron to move from one covalent bond to the other. So in other words, to make it easier for holes to move through the crystal. And the mobility of holes is actually approaching the mobility of electrons now, in that case. Because if you compress a crystal and make the atoms closer, more closely spaced, it becomes harder for electrons to move through that. Right? But generally, for every single semiconductor, the hole mobility is always less than the electron mobility. Okay. Other questions? Okay, great. All right, so a semiconductor that's pure is useful, but not as useful as if you can selectively change its electrical conductivity in a controlled manner. So one way we do this is with introducing impurities, small quantities or small percentages of impurities into the single crystal. So we do this this is called the process of doping. So the doping means that you substitute a silicon atom with an impurity atom. So it's either in silicon, it's either from column 5 of the periodic table, okay, or column 3. So let's talk about column 5 first. So these are, okay, so when you substitute a phosphorus atom for silicon so that the phosphorus atom is bound covalently to 4 silicon nearest neighbors, phosphorus has 5 valence electrons. So only 4 of them will be participating in covalent bonds with its nearest neighbors. And you have a 5th one that's really not participating in a covalent bond. It's not really bound tightly to or attracted tightly to the silicon atom. So it's very easy for it to just wander away. In other words, it's easy for this negatively charged electron to wander away, leaving behind a net positive charge at that lattice site. Okay? So because it leaves an ionized atom behind, we call this process ionization. Okay, so this atom will donate an electron to the silicon lattice. And so we call column 5 elements in silicon donor atoms. And if you look at the periodic table of elements, arsenic is another species that is in column 5. And phosphorus and arsenic are the most commonly used N-type, or sorry, donor atoms used in silicon. And we call them N-type dopants because they contribute negatively charged mobile carriers to the silicon lattice. So now the electron that's freely moving around in the lattice can contribute to current conduction in the semiconductor. And we typically keep track of we control the concentration of electrons by controlling the concentration of donors in the semiconductor. So typically, the range is anywhere from 10 to the 15 per centimeter cube to 10 to the 20 per centimeter cube. That's the dopant concentration. Okay. Now, does anybody remember from the first lecture what is the atomic concentration of silicon? 10 to the 10. Wait, that is a number from the first lecture. Very good. It's not the one. Not the 5 times 10 to the 22. Actually, that's a good point. 10 to the 10. That sounds like a lot. 10 to the 10 electron hole pairs naturally exist at room temperature in silicon, but the total atomic concentration is 10 to the 22. So 10 to the 10 out of 10 to the 22 is very small, right? So actually, at room temperature, a very few number of electron hole pairs, percentage-wise, exist, and that's why silicon is actually a good, reasonable insulator at room temperature. Now, if we want to make it a conductor, we have to increase the concentration of electrons or holes, and we can do that by adding dopants. So let's say if each dopant contributes 1 electron, you can have 10 to the 15 electrons per centimeter cube, or up to 10 to the 20 electrons per centimeter cube. Okay, so if the concentration of atoms is, let's say, 10 to the 22, then that's like up to 1 in 100 atoms that are replaced by a dopant. Right, so it's still a small percentage. It's less than 1 atomic percent typically that we dope the semiconductor. Okay. Now, if we want, for whatever reason, to have a semiconductor made very electrically conductive, but to have the conduction performed by positively charged holes, we can add an element from column 3 rather than from column 5. Actually, I wanted to ask, so you know that model of Peng, modeling standing up, generating an electron hole pair. What would be, following that analogy, what would be a good model for a donor atom? Considering that one of your desks, with you sitting in it, is a good model for a silicon atom. Desk. Well, what kind of desk would tend to easily donate a person? Like one of these. There's no table. So it's easy to get out, right? So it's different, right? It's different from a regular desk. So donor atoms are slightly different, but they fit in place, and it's easy for them to lose. They don't care. I mean, it's easy for them to lose the electron, just like a person can easily get out of a chair without a desk attached to it. Okay, what about column 3? Column 3, you have only 3 valence electrons. So that's boron. Example, the most commonly used dopant, acceptor dopant, is boron. Okay, and we call them acceptors because they only have normally 3 atoms in the valence shell. So 3 electrons participate in covalent bonds with nearest neighbors. And they really would like to they would really welcome another electron to come from a neighboring covalent bond to come fill this site so they can have 4 covalent bonds to nearest neighbors. So an acceptor atom, such as boron, if it's sitting in if it's substituting for silicon in the crystal lattice, it will actually naturally want to attract an electron to form a covalent bond with the nearest neighbor. So basically, it likes to accept electrons. Now, when boron accepts an electron from a neighboring covalent bond, it's creating a half-filled covalent bond. In other words, it's creating a hole. Okay? So every time, ideally, you introduce a boron atom into a silicon lattice site, you are actually contributing a hole to the silicon lattice. Does that make sense? In other words, you're taking away a conduction electron from the lattice. Okay, so what kind of a seat would actually be a good model for an acceptor atom? Pardon me? An empty desk. Well, an empty desk is like a hole, let's say. So I was thinking, oh yeah, do you have a good idea? A comfy chair, exactly. So have you been out in the Moore room? They have like these huge bean bags, right? So that's like a comfy chair. It's like if you're sitting there, it's easy for somebody to say, oh, let me just sit down and relax, and it's hard to get out. Have you ever tried to get out of a bean bag chair? So an acceptor is kind of like a big comfy chair. You're right, like a bean bag, I think. Right? So think of the bean bag model. It wants to accept an electron here. It's happy to see you leave, Okay? And same thing, typical concentrations in an integrated circuit device is anywhere in the range 10 to the 15 to 10 to the 20. Now, I mentioned that the high end is about 1 atomic percent. How about at the low end? What percentage does that represent? How many parts per million? 0.1, yeah. So it's actually a very small percentage. So semiconductor manufacturing is a highly precise process. You have to be able to control impurities to a level, less than 1 part per million, typically even down to 10 parts per billion. So that's one reason why it's expensive to build a manufacturing facility, because you need to be able to control contamination or avoid contamination very, very strictly. Okay? So terminology here, capital N sub D is what we use to indicate the concentration, so number of atoms per centimeter cubed for donors, and N sub A is the concentration of acceptors, okay, per centimeter cubed. So keep in mind, it's centimeters, okay, is the length unit that we use in this class. Okay, so I think we already, well, this should be obvious. So here's an illustration of arsenic with this extra electron. I guess I shouldn't draw a hole. Sorry. All right. So we've already gone through this. But the electron easily goes away to become a conduction electron. And when that happens, then the arsenic has a net positive charge. Okay? But the ion that donates an electron is not mobile. It's actually fixed in the lattice, right? It's like bound to its four nearest neighbors. So you have immobile positive charge and a mobile negative charge that can move around to contribute to conduction. The arsenic does not contribute to conduction directly. Okay? With an acceptor, you can have an electron move from a neighboring covalent bond to help boron satisfy the desire to have 4 covalent bonds to its nearest neighbors. So that creates a hole, and that hole is mobile, but boron becomes net negatively charged, so it's ionized. And again, boron is fixed in the lattice. It does not move. It's immobile, but the hole itself is mobile. Yes, question? Okay, so the question is, can the arsenic capture an electron? Yes. So the question, okay. Yes, yes. Okay, so the question is, well, is it possible for an electron that's wandering around the lattice to come by the arsenic atom and then just get trapped there? And the answer is yes. And that can happen, but what happens is that, okay, what's the density of these electrons that you're contributing to the lattice? Yeah, it's like less than 1%, right? So the number of electrons per atom is pretty low, so what's the chance of an electron that's wandering around randomly in the lattice meeting up with that ion and then just being attracted to it and staying there? It's not going to happen very often. And then also because it's not held very closely, to the arsenic atom, the nucleus, it can easily escape again. So it does happen to get trapped, but it probably faster than the time it takes to trap an electron, it reionizes itself. At room temperature, that's what happens. But you're right. So later, in a few more lectures, we'll talk about trapping and detrapping. So actually, that's a good lead in here. Okay, wait. Okay, I'm going to come back to that. But let me just cover this slide here. This is sorry, this is a kind of a complicated chart, but it's a chart showing the solid solubility of dopants in silicon. So during the integrated circuit fabrication process, what we do is we introduce these dopant atoms into silicon in different regions in well-controlled quantities. And in order for them to contribute an electron or a hole to modify the electrical property of the silicon, we have to get those atoms to sit on a lattice site. Right? They have to sit on a lattice site to bond with four nearest neighbors. And so to do that, we actually have to heat up the silicon to very high temperature and get the atoms to move around and actually form bonds. Okay, so typical process temperatures are above 1,000 degrees Celsius, peak temperature. And so this plot shows the solid solubility of various dopants as a function of temperature in silicon. So the most significant dopants to notice are arsenic, phosphorus, and boron. Okay, so if you look at this chart, you have increasing solid solubility to the left. So if you want to have a large number of dopants to be able to substitute for silicon, you want a high solid solubility. So these three dopants, phosphorus, arsenic, and boron, actually have high solid solubility, so you can actually incorporate a larger percentage, up to 1 atomic, or more than 1 atomic percent in silicon. And so that's one reason why they are the most commonly used dopants in silicon. Okay, all the other dopants here have much lower order. This is a log scale on the horizontal axis, so you can't really get nearly as much of the other dopants into silicon. Okay? Another requirement of the dopants is that, well, when we make an integrated circuit, you have to heat it up to get those dopants into the lattice sites. But you don't want to have random thermal motion cause those dopants to diffuse away, from the place where you place them, right? You don't want them to wander away when you heat it up to 1,000 degrees Celsius. So, so basically, that's another consideration. Not only the solid solubility, but diffusivity, the diffusion constant or diffusion rate of dopants in silicon also determines which of these dopants are more attractive to use. Okay, so let's talk about this energy trapping and detrapping. Okay, so if we go back to the band model, okay, again we have an allowed energy states up here, allowed energy states down here. The dopants have some local allowed energy state for that fifth electron, right? So there's some energy level associated with that fifth valence electron for the donor. And it's very easy for that fifth electron to become a conduction electron. So that means that energy level of that donor electron state has to be close to the conduction band edge. Right? So it's very easy for an electron, which is one of the 5 outer valence electrons of the donor, to just escape and move around in the lattice. That means it's occupying the conduction band. Or does that make sense? So we know that any donor electron energy level has to be close to the conduction band edge in order to allow the donor atom to ionize very easily. Okay? So what is the reason why I'm drawing it here as a dashed line? These energy levels of donors are dashed lines. They're not uniformly spread throughout the semiconductor. Right, there are very few of them, right? There's only at the most 1 in 100. So only occasionally you'll see a donor atom, even in the most heavily doped case. And so they provide energy levels, sort of discrete energy levels, spread throughout the silicon lattice. Not like the silicon atoms. There's this periodic, regularly bonded silicon atoms. They each contribute energy levels, and the energy levels are all shared throughout the lattice. but the donors only exist in certain locations. So we call these localized states. Right, so this is like a localized energy state. Right, it's an allowed energy level for electrons to occupy if they're right there where the dopant atom is. Okay. So if an electron's wandering in the conduction band, is wandering around the lattice, once in a while it'll see that localized energy state and can fall into it. But then easily, because of the thermal energy, random thermal motion, you can easily escape and go back to the conduction band. Okay, so that energy needed for an electron to leave the donor atom is just the ionization energy of the donor. Similarly, for an acceptor, it's very easy for an electron in a neighboring covalent bond to come and form a covalent bond around the boron, let's say the acceptor atom. So basically that means it's very easy for an electron in the valence band to move up and become immobile. It's stuck there with the boron atom. So it occupies a local energy state. It's no longer occupying like a valence band energy level that belongs to the entire lattice. Okay? Does that make sense? So that's acceptor ionization energy. So typical ionization energies, KT represents roughly the average amount of kinetic energy that a particle has at a certain temperature, and that's 26 millielectron volts at room temperature. So these ionization energies are within a couple of KT so relatively easy for electrons to gain enough energy to move like from the valence band into the acceptor energy level or from the donor energy level into the conduction band. Okay? I'll just mention this is the answer to a question right now for the homework. Indium actually is also one of the becoming more popular to be used in integrated circuit devices today. Not because it has a low ionization energy, but because it has a low diffusivity. So when you process a semiconductor device, if the devices become very small, that means they also have to become very small, not only in lateral dimensions, so you can fit many of them on a chip, but they have to become very shallow in doping profile. So you really don't want to have dopants that you introduce, diffuse into the silicon too far. And indium has a relatively low diffusivity, so it won't move far from where you place it in a semiconductor. So it's actually desirable for that reason to be used in integrated circuit devices today. But anyway, so the answer to one of your homework problems, boron and indium are the common p-type dopants. In other words, they introduce positively charged carriers into your semiconductor sample. Okay, so now the dopant ionization, as I mentioned, KT, that's 26 millielectron volts at room temperature. Well, if you're at much lower temperature, you won't have electrons won't have sufficient kinetic energy or enough thermal energy to escape or to move from even the valence band energy levels to the acceptor localized energy level. So only as you heat up the integrated circuit or the semiconductor device will you start to see more and more ionization of carriers. Okay, so only at room temp. So today devices operate over a wide range of temperature, but at room temperature, in this class, we can just assume pretty much nearly 100% of all the dopants are ionized. In other words, you can assume that every single acceptor contributes a hole. Okay, so the number of holes is equal to the number of acceptors, and the number of conduction electrons is equal to the number of donors. Okay, I have to qualify that. That's only when you have one type of dopant in the semiconductor. If you have both types, it's a little bit different. Okay, so let's talk about that. Charge carrier concentration. So as I mentioned, every time a donor donates an electron, it becomes ionized and is positively charged. Right? An electron is negatively charged. So the concentration of electrons and donors should be initially the same. Every time an acceptor accepts a covalently bonded electron from the neighbor, becomes negatively charged, and that process creates a hole that's positively charged. So we have some mobile charge, and you have immobile charge. The ionized donors and acceptors are immobile. So only the mobile charges contribute to electrical conduction. Okay, but basically, when you dope a semiconductor, you're not changing the total charge in the semiconductor. The total amount of positive charge and the total amount of negative charge is equal. Okay, that's what we mean by charge neutrality. Okay, so what happens when you dope a semiconductor sample so you create a lot of electrons? Well, it turns out that the product, n times p, so the density of electrons times the density of holes, is always going to be equal to Ni squared. Ni is the intrinsic carrier concentration that we introduced at the end of last lecture. Okay, so this is the so-called, sometimes it's analogous to the law of mass action in chemistry. Okay, so let me just explain it. So let's say if Peng were modeling an electron, and most of these seats in the classroom were empty, it's really easy for him to just sit down, right? Easily to find a seat, and then you'd basically annihilate the electron. In other words, if there are a lot of holes, then the chances of an electron recombining with a hole go up, and so the concentration of electrons goes down. So you basically, if you increase disproportionately one, like p, the concentration of holes, you're going to decrease the concentration of electrons, simply because anytime an electron and a hole come together, they recombine, and you end up with nothing. I mean, no hole, no electron, no conduction electron. Okay, so it just turns out that the product at equilibrium has to always equal to the product of the intrinsic carrier concentration squared, right? Because for a pure semiconductor, the concentration of holes is Ni, and the concentration of electrons is Ni. So the product of N and P is Ni squared. So it just turns out that no matter if you dope it or not, the product is going to be Ni squared if you're talking about a semiconductor material in equilibrium. That means you're not shining light on it, you're not applying a voltage or a magnetic field to it. Okay? It's just natural. So if you take these two equations, the charge neutrality condition and the thermal equilibrium law, you can derive these. This is the binomial formula, I guess. You can derive these equations to tell you what the concentration of electrons and holes is in your sample if you know the concentration of donors and the concentration of acceptors. The key thing here to notice is that you have in each of these differences in dopant concentration. So if you have a material that has both dopants and acceptors, okay, dopants will donate electrons, acceptors will donate holes. Let's go back. So if you have, what will happen? So basically, let's say you have this, on the lower right here, you have a sample that has a lot of acceptors, so you have a lot of holes. What if you added a lot of donors? So you suddenly add a lot of electrons. Well, those electrons that are donated can move around the lattice very easily and recombine with the holes, right? The chances of an electron meeting up with a hole will go up if you increase the electrons concentration a lot. So basically what will happen is that electrons will end up recombining with holes, and in the end, whichever one has a higher concentration will dictate if you have more holes or more electrons. So if ND is greater than NA, that means you have more donors than acceptors, then you'll end up with overall more electrons than holes. Conversely, if you have more acceptors than donors, then you'll end up in the end with more holes than electrons. Now, okay, let's review. What is the typical concentration of dopant? What is the smallest typical range of dopant concentration? 10 to the what? 15. Very good, John. And what is Ni squared at room temperature, where most integrated circuits operate? 10 to the what? Ni squared. Okay, but let's compare it with dopant concentration squared. So let's compare Ni with Na minus Nd typically. So we know that Na minus Nd is typically at least 10 to the 15. And Ni is 10 to the 10. So what does that tell you? This term is usually, the Ni squared term is usually negligible compared to the first term underneath the radical. Okay? So this equation might look a little bit unwieldy, but it's actually pretty simple. Okay, so key here, net dopant concentration. So common mistake is like, okay, you add dopants, donors, and acceptors, you end up with 10 to the 20 holes and 10 to the 20 electrons. That can't be the case because the product of N and P has to be equal to Ni squared. Okay, so just be careful. So basically, okay, let's look at this case. Let's say a material, let's say Nd is greater than Na. Okay, so this term underneath this radical on the second equation here is positive as much greater than Ni squared. Okay, let's just do that as a simple example. Let's say it's 10 to the 15. Oops, 15 per centimeter cubed. Okay, so this is 10 to the 15 over 2 plus, okay, if this is 10 to the 5th, if this first term here is 10 to the 15 over 2 squared, it's still much greater than Ni squared. So this is approximately equal to the square root of approximately. Okay, so in this class, okay, in engineering classes, we don't keep track of too many decimal points. So, you know, like, this is very accurate already, right? So basically what this means is essentially the concentration of holes is going to be just dictated by the net dopant concentration when the net dopant concentration is in favor of acceptors. Okay? So that's P. What about N? The law of mass action. N is going to be 10 to the 5th per centimeter cubed. Right? Well, okay, this is all an approximation, but yes, well, yeah. So this is basically all you need to do, like, for this class in terms of accuracy, okay? Because orders of magnitude, like anything more than 10x difference, we can assume is negligible for calculation purposes. Okay, so let's do let's do the opposite case. Nd is greater than Na, and specifically the difference is much greater than Ni squared. Okay, actually well, let's just do that. So let's say let's say 10 to the 17 per centimeter cubed phosphorus. Okay, that means Nd equals 10 to the 17 per centimeter cubed. And let's just assume Na is 0. Okay, so tell me then, what is going to be N based on what we just did in the previous slide? 10 to the 17. Very good. And what will be P? 10 to the 3rd per centimeter cubed. Okay? Great. And we already did that. Okay, so one thing, just to reiterate, the temperature. This is a plot. This is a little bit confusing. I've got it from Pierre. But basically, this is a plot of the electron concentration normalized to the dopant concentration. Okay, so 1 means that all of the number of electrons equals the number of donors. So at very low temperature, what happens is that the thermal energy is not enough to cause, you know, the donors to ionize. So the concentration of electrons drops to 0 as you cool down the semiconductor. This is in temperature in Kelvin. So this is typically well below the temperature we operate in an integrated circuit, a normal consumer-based integrated circuit. So this phenomenon is called freeze out. That means, you know, it's so cold, the electrons don't even have enough energy to escape from the donor, so the donor doesn't become ionized. So the concentration of electrons available for conduction just drops with temperature. Now, around room temperature and even above for a few hundred degrees, every donor donates an electron, and the concentration of the intrinsic carrier concentration the concentration of electrons that have enough energy to just, 1.212 eV, just go from the covalent bond just to become a free conduction electron. That's very small. But once you heat up a semiconductor to very high temperature, you'll get more probability that electrons can just directly come out of covalent bonds. And so the concentration of electrons will start to be dominated by the intrinsic electron concentration rather than the dopant concentration. So typically, we want to operate semiconductor devices in this extrinsic region where the properties of the semiconductor are not the normal intrinsic properties. We want to be able to control the carrier properties by doping it or whatever. So we typically want to operate integrated circuits in this flat region where we can actually precisely control the mobile carrier concentration, let's say, for example, by doping precise amounts into the semiconductor. Okay? So this illustrates what happens. If you heat it up too much, electrons can go directly into the conduction band from the valence band, and you get carriers. Material's electrically conductive. You can't really make a transistor out of it because it's always conductive. You can't turn it off, and so on. Okay, so this is a summary of the terminology. Donors, acceptors. N-type means more negatively charged mobile carriers than P-type means predominantly positively charged mobile carriers or holes. Majority, so remember in the example here, the simple example, there's a huge difference in the concentration between electrons and holes. So we can say electrons are the majority carriers in this example. Holes are minority carriers in this example. And in the previous example, it's electrons that are minority carriers. The holes are the majority carriers. Okay? All right. So that's the end. We're out of time. But I'd like to remind you, you're welcome to join me for a break outside right here in the student lounge. We have some refreshments starting up there. And yeah, it's a nice day, nice weather. Hope to get to know a lot of you throughout the semester. All right? So we'll see you Thursday.